All right. So we're continuing our kinematics using good problem-solving techniques. And developing an awareness that way, a physical intuition, stuff that is not obvious. It took thousands of years for people to wake up to, and if you go about your daily life, you don't have it. One process that really works to do this is a standard process that we analyze where we take an object and we throw it or we drop it. So just drop or toss. We call them projectiles once we release them. It's not this process while I'm throwing it, but once I release it, we call it a projectile that has been projected. Dropping is also a projectile. That is a special case, and we're working with negligible air resistance. Air resistance is a tricky thing. If you can intuit it easily by sticking your hand out the window of a moving car and you go faster, clearly you get more air resistance. If you expose less area, you get less air resistance. So there are variables. Modeling that mathematically can be tricky, leads to differential equations. We will touch on it a bit. But for a lot of problems, it serves us to have negligible air resistance, so don't go dropping feathers or cotton balls, just things that don't get affected too much. To say there's no air resistance, you better mean it's in a vacuum. To say things are massless is kind of a loose, sloppy way. You could have negligible mass, negligible friction, negligible air resistance. It takes more, but it's more correct. And there's no propulsion, no wings, no jets. Okay? So that's what we mean by projectiles. So what can you do? So here's a few cases. A lot of times we don't think generally. We can drop it. If you drop an object, what's the velocity? 0. So dropping implies that initially it's 0. Here, velocity is 0, and the acceleration is 0. The moment I let go, in reality, it starts sliding first, but if I can instantly let go, the velocity is 0, but it does have a non-zero acceleration. Okay, or you can toss it up. So this is not the free flight, or we'll talk about, but once I let it go, then it is. And we'll do this process in the next video. So you can toss it up, let go, and then you can look at it at any of those moments in time. Okay? Or you can throw it down. And once you let go, then it is in this category of negligible air resistance projectiles. You can toss it horizontally. You can toss it up or you can toss it down. And once you let go, it takes off. So obviously you can take it. But all those are projectiles. So those are commonly called free fall. I find for people that are just getting used to this, you know, you go fall, wait, free fall, it's going up. But this is, all these are called free fall. So to avoid that, I use the term free flight. So whatever, it doesn't matter, and no one else will know what you're talking about but us, but free flight. The beauty is it's FF. And so once you let go, you have a certain acceleration in free flight of AFF. Now if you're on Moon, it's different. If you're on Mars, it's different. Here on Earth, it can vary a little bit from place to place and depends on how precise you need to be. So how much is AFF? Well, as we know, the direction is down, because on the way up, you decrease speed. On the way down, you increase speed. So it's down, and we know the value is g. G is, of course, plus 9.8, and that could be 9.80, 9.81, 9.79. I'll just say that. Or, 2 sig figs, meters per second every second, or meter per second squared. Okay, fine, you got that. So this value is g. Down, if you call up positive, then the acceleration in free flight is negative g. If you call down positive, then the acceleration in free flight is positive g. You don't really need the positive, but just to be careful. Nonetheless, the Earth doesn't care what you call it. It's still down with this value. Meaning it's going to, as it goes down, it's going to pick up about 10 meters per second every second, which is about 20 miles an hour every second. On the way up, it'll lose that much. When you go over, that's going to be interesting, and then we'll get to that soon. Are we cool with that? Let's do this then. So what we're going to do is again, use our good problem-solving techniques for kinematics. And the kinematic case here is over here. We do this as a lab. We can drop a brain or a baseball. The vote was to, we got baseball in the brain, it's almost spring. So the vote was to drop a brain, and we're going to drop it. So right now the acceleration is 0. You know, just look at it. Like sometimes people try to do memory. What's the acceleration? It's not g, it's 0. When I let go, it'll kind of slip a little bit, and then it'll fall. 1 meter. Let's see if the baseball does it. Does it take more time, less time? With negligible air resistance, it's going to take the same time. With air resistance, obviously a feather would take longer. So in this model, we've got free flight. So let's analyze this with our problem-solving techniques. Without worrying about even what I've measured, let's just say, what can I say in this case? So in this case, let me draw the process. Remember, the first thing to do is to visualize the process we just did, and then we're going to slowly read the problem or look at it and visualize and sketch it. So visualize, sketch, and this is good to do this as a habit until you're there, but show all the states of interest, show your coordinates that you've chosen, which way is positive, and show your variables. Okay, so this is kind of easy, right? I'm interested in my first state, right, when I let go, so it's free flight, if you will. And then I'm interested not after it hits, because that's not a projectile. I'm interested in just before it hits. So I'll put an arrow there, and I'll call that state 2. 1, 2. Now, of course, I can look anywhere in between. After it's dropped 10 centimeters, how fast is it going? And we can analyze that. So you can break it down anywhere you need to. All right, so that's pretty much the process. Let's say I've shown my states. That's good. The coordinates, it's up to you. Personally, if it doesn't go up, why would I call up positive? I'm going to call this down. I'll call it y, as commonly we do. And then I'm going to put the acceleration next to it. Ay is equal to, and we know that in this case, ay is equal to positive, which means down, g. Okay, cool. And G, again, G is always a positive number. So that's the process. That's pretty much what I know. Other variables that I should know. Well, I could do height. This is the ground. Often I just care about the change. So I'm going to go like here to here. And notice that from here to here, now this is something people often mess up. That is delta y from state 1 to state 2. If I chose up positive, that would be a negative number. Since I chose down positive, that's positive, and that's positive. This, just going little by little, will help you read the problem and avoid all kinds of time-consuming and frustrating mistakes. Now, what do I need to do? Well, I can kind of sort my data. What do I know? I've got given, I've got what's implied, and I've got what I want. Now, I haven't stated what I want or what I'm given. So let's see, what's implied here is that I'm in free flight, so the acceleration is free flight, or A is equal to A free flight, if you want. In this case, plus G, we can write that symbol, but we might be looking for G. So we'll see. The other thing that's implied is that I dropped it, so that V1 equals 0 is implied. And we can then look for any of our kinematics things, like how fast is it going, or how long did it take, or anything like that. So that's it. That's our second step. We did quick visualization. We laid it out. This one's kind of easy. We get more one. The general method then, so general approach, as I said in the last video, you have definitions, which you could start with. Some people think that that's a better way. Just start with the definitions, and that can work. The graphs, or the constant acceleration equations. I like to go here. I'm going to say in general, I've got delta y from states, earlier to later is equal to the velocity at the earlier moment, delta t earlier to later plus 1/2 the acceleration, delta t earlier to later squared. I've got the velocity later is velocity earlier plus acceleration, delta t earlier to later. I got v later squared is equal to v earlier squared plus 2a delta x earlier to later. This will save me, though cross-checking and redundancy will help avoid mistakes. Okay, so that's the general method. I also have V average is V earlier plus V later over 2. And that may or may not be useful. Okay, cool. So now I want to solve it. I don't really know what I want to solve, so I'm just going to do this generally and then stop it there because you can play with it. So to make this specific, that's my general. I've chosen to use constant acceleration equations. I just write them without thinking ahead. What slows people down is they think ahead. Write it. You have a thought, write it down, then think. You can see more clearly. You can see more clearly if you move the puzzle pieces around. So make this specific. All right, let's do that. We ask ourselves, what do I know? Let me think physics. So let's do this in purple. Getting a little messy. I want to make this quick. So specifically, I have delta y, and I'm going, let me do this. I really recommend, because sometimes in a problem you look from 1 to 2, then you look 2 to 3. Maybe you look 1 to 3. Maybe you look 4 to 9. That would be weird, but okay. So delta y, 1 to 2, is equal to v1. People often get that confused. Which v is that? The time from 1 to 2 plus 1/2. Now, this is g. I call that, and it's positive g. If I call up positive, then this would be negative g. But here the acceleration is g. That is not gravity. G is not gravity. People call it gravity. It's wrong. It's not gravity. It's the free flight acceleration. Now you could say acceleration in free flight. You could say acceleration when there's only the force of gravity due to the largest astronomical object that you're on, or not. Or you could say free flight acceleration, or free fall, that's fine, but I like free flight. That is acceleration, it's not gravity. G is the symbol we use. All right, delta t 1 to 2 squared, cool. V2 is equal to V1 plus G delta t 1 to 2. I can combine those algebraically. V2 squared equals V1 squared plus 2. What's the acceleration? G delta what? Not x, y, because I just chose to use y. We commonly do. And there you go. And you can do V average is V1 plus V2 over 2 as well if you want. V average V1 plus V2 over 2. Okay, so it's that simple, these kind of problems. You can write each of these steps quickly, but thinking all of this in your head is like solving the puzzle without touching the piece. So get used to go from one step to the other. Play the song and don't skip a note, but do it up to speed. What do I know? I don't know. I mean, I could measure the delta y. I could measure, oh, look at that. We look for zeros, make life easier, right? Hey, I didn't need to write that at all, did I? And I didn't need to write that. And I didn't need to write that. And I didn't need to write that. Okay? So now I've made it very specific to the case at hand. How do those puzzle pieces fit together? I don't know, just move them around and see how they go, but be organized and see. There's no magic, there's no memory, yay, right? It's that, I don't know, all I need is this. So if I measure how far it falls and the time, I can evaluate G on my planet. On Mars, it's about a third of what it is here. On Moon, it's about a sixth. On Mercury, it's about a third, which is an interesting thing. So if I have the time and I know G, I can know the velocity straight away, right? Sometimes I need to combine things. If I know G, if I assume that it's the 9.8 or 9.81 and the delta y, I can figure out the velocity here. Check the units work. You know, anything. And we're good. So whatever you want to measure is data or given data, and then whatever you calculate. And we're good. Let's do a harder problem. Let's throw up.